Hey everyone, Dr. Carroll here in Physics 40S land. Welcome to the first lecture of Unit 3. Unit 3 is going to focus on more forces. We're going to introduce the force of friction. Hope you don't resist that too much. We're going to look at breaking up gravity into parallel and perpendicular components. When we look at inclined planes, that's a bit of a slippery slope. We're going to look at the spring force, which is a restoring force, so you'll get a bounce out of that. And then we're going to look at centripetal forces, so uniform circular motion. So those are the four topics that we lump together in Unit 3. Now there's lots of forces. It's a bit arbitrary where I decide one unit ends and the next one begins, but it's essentially I want the same amount of material in each one, give or take. And when all is said and done, you're going to learn a lot of forces, and the force will be with you. So I'm going to dance back and forth between our booklet of notes and our mini text. I'm going to the mini text here and look at friction, and we see here that you have microscopic welds, little bits of molecules that stick out depending on the material and how much you press against that material, and what the material is going to affect the friction. Okay, so the magnitude of the frictional force is determined by the type of materials in contact and by the normal force exerted by one object on the other. And the equation we're going to use for friction, and some of you have looked at this in Physics 30, and you may have heard the expression friction is fun, because you got a little f, you got the Greek letter mu, which I know we use for micro, we also use for bond dipole in chemistry, and molecular dipole as well. And then we got the n for the normal force. So here we're using a lowercase n for normal force. So you see F-U-N, friction is fun. Okay, so that's a way to remember the symbol. So my coefficient of friction, if things are moving, it's kinetic. If not, it's static. I'm just going to say coefficient of friction is the force of friction over the normal force. And there's no units for the coefficient of friction because friction is in newtons, normal force is in newtons, so the units cancel out and the coefficient of friction is no units. The coefficient of friction is greater than 0 and less than 1. And the closer it is to 0, the more slippery is the surface. Okay? And then let me jump to the picture here. We have here that a lawnmower is being pushed by a force of 150 newtons horizontally and 40 newtons down. If the kinetic coefficient of friction between the wheels and the grass is 0.9, find the force of friction acting on the lawnmower. Okay, so here I use Josie. I think I was watching the Archies, Riverdale, everyone's favorite show. And Josie's pushing with a lawnmower. I don't know, maybe it's canceled by now, who knows. 12 kilograms, and the coefficient of friction is 0.9. So there's Josie or Jose or whoever you want it to be. You can draw a picture of yourself, why not? Pushing the lawnmower, and the lawnmower has a mass of 12 kilograms. So the force of gravity for the lawnmower is going to be mg, so 12 times 9.8. Let's punch that out here. 12 times 9.8, 117.6 newtons. Okay, so that might be useful for something. What else do we know? We know that the person is pushing horizontally with 150 newtons and down vertically with 40. So it's at an angle. So if you really wanted to get that applied force, you could take 150 and 40 and get that value. But it's already in components, so let's not bother to do that. Here's the free body diagram. So we want to get the force of friction and the acceleration of the lawnmower. So the vertical, we have static equilibrium. You aren't lifting the lawnmower into the air. I don't know, sometimes when the grass gets really high, you do that, don't you? That's dangerous. Don't do that. So normal force is going up, and then you got gravity, and you got that applied vertical force by the person going down. So the normal force is going to be Force of gravity plus 40. Force of gravity is mg. We already got that. 117.6 plus 40, so 157.6 newtons. So the normal force is that value. Why do I care? Why do I need the normal force? Because that's how I'm going to get friction. Friction is mu times the normal force. So friction is never going to be more than the normal force. It is related to the normal force by mu. Mu here was given as 0.9. So things were pretty dry. If it's more slippery, mu would be smaller. But typically you want to mow the lawn in drier conditions anyways, right? So the force of friction is 0.9 times 157.6. So you get 141.8 newtons. And that's your force of friction. Now, your acceleration. Well, my net force, I got 150 to the right, and I got friction opposing it. If friction is more than 150, then you ain't going anywhere. But it wasn't. It was 141.8. So 150 minus 141.8 is 8.2 newtons. So my acceleration of the lawnmower is 8.2 newtons over 12 kilograms. Where's the 12 kilograms? Oh, that's the mass of the lawnmower, 12 kilograms. So 0.68 meters per second squared. So this is a typical question. You draw a free body diagram, you get the normal force first, and then you can get the force of friction, and then use the free body diagrams, chop things into vertical and horizontal, and take it from there. Okay, let's go back to the mini text and see if there's anything else that they have to say about that. Oh, they have a nicer picture, don't they? They have an actual picture of a lawnmower in a circle, and they show all the arrows. So you can certainly look at that and go through it in more detail. Example 9 is the actual acceleration. Okay, let's try this next one just using the mini text. It's going to be the same thing, but it's a nicer drawing. So here, very exciting, someone is taking a chalk brush and a dry eraser now in today's lingo, and pushing it up the whiteboard. And so they're pushing it up at 6 newtons, and they're pushing in at 2 newtons as it goes up. We want to find everything we can about it. So going up at 6 newtons, well, gravity's going down and friction's going down because friction opposes the motion. You're pushing in at 2 newtons, so my normal force has to be 2 newtons. You're also given the coefficient of friction, 0.4. Don't worry about the K. Yeah, I know it's moving, so it's 0.4. The mass is 0.5. So in the x direction, well, it's 0. So my normal force is 2 newtons. Okay, and you aren't pulling the chalk brush off the board or shoving it through the board. The force of friction is mu times F normal. So 0.4 times 2 is 0.8 newtons, and that's an N. Sometimes I use uppercase N. Doesn't matter. So then that's 0.8 newtons. So that is the force of friction, 0.8. Force of gravity is a half of 9.8, which is 4.9. So I got 6 going up and 5.7 going down. So I got a net of 0.3 going up. So my acceleration is my net force is F over m, so 0.3 over 0.5, which is 0.6 meters per second squared going up. Okay, let's try another one, just straight from the mini text here. We're having a hockey player, maybe he plays for the Jets, I don't know. Is there hockey now? I don't know. A puck of mass 0.3 kilograms is sliding along an essentially frictionless patch of ice at 6 meters per second. Then the puck encounters a rough patch, don't we all, of ice with a coefficient of kinetic friction of 0.1. How long will it take for the puck to stop, and how far will it travel? Okay, so it starts at 6 meters per second. Now we want to know how far it travels, so when does it stop? It stops at 0 meters per second. The mass of the hockey puck is 0.3, and once it encounters the rough ice, it starts to feel friction, 0.1. So still not lots, but it's a bit. So what kids get tripped up a bit is just getting the free body diagram, because they think that the person's hit the puck, so there has to be a force going to the right. Well, there isn't. The puck's already been launched. So you're now looking at it once it's been launched. So the only force in the horizontal is friction, causing it to slow down once it hits the rough patch. The gravity's going down, normal force is going up. It's sliding along the ice. It's not flying through the air. It's not a wrist shot, something like that. So in the y direction, the normal force equals the gravitational force, which is going to be m times g, 0.3 times 9.8, 2.9 newtons. So that is my normal force. The friction force is mu times the normal force, so 0.29 newtons. So my x component, force of friction, is minus 0.29 newtons, right? It's opposing the motion, so that's why I have a negative sign there. So that is my net force, negative 0.29 newtons. Now I can get the acceleration. It is going to be negative 0.29 over the mass of the puck, negative 0.97 meters per second squared. Now, how long does it stay on the ice once it hits the patch? So 0 minus 6 over minus 0.97. Delta T is V2 minus V1 over the acceleration. And the friction is causing a deceleration, right? So it takes 6.2 seconds. Notice how the negatives have canceled to produce a positive time. To find the distance traveled, you could look at the average velocity, so 6 over 2, 3 times 6.2, almost 19 meters. Okay, 18.6, so it rounds off to 19 meters. Okay, then those flow charts, you can look at them on your own. And let's go back here and see, I'm in the booklet here. There's the chalk brush example, there's the hockey puck example, and you can try on your own, page 188, number 38, 42, and 49 to get more discussions of friction. Okay, so that's good for our first lecture in Unit 3. So hope it didn't rub you the wrong way.